properties of logarithms down the road. That's why you learn about logarithms. All right. So with this equation, we're going to go ahead and distribute. I'm going to do that first. I don't know why, but my shade isn't as interactive on this slide because probably of my little animation. So I'm going to take and distribute the 2 and the 3 there to those terms. It's going to look like this, just to get rid of some of my parentheses. 2 is distributed into these terms. The 3 gets distributed into these green terms, 3 there, 3 there, and then that negative sign is distributed to everything that's in the brackets over here. So you got negative that, negative that, negative that, and negative that. Everything that has a plus sign is now changed to a negative because it's subtracting that entire quantity. You with that? Distributing. I'll pause just a moment. At this point, I'd like to start combining some of the terms. You see this, this, and this. Can you give that a new name? What would be the free energy of NH3? Let me write the chemical equation back up here. 3H2s plus N2 yields 2NH3. I have the free energy of NH3 times 2 minus the free energy of H2 times 3 and minus the free energy of N2. Can we give that a new name? Anybody see it? Go ahead. That's delta G. The products minus the reactants. So these things that I circled, I could just rename that part as delta G. And because we're adding and subtracting all these terms, it doesn't matter what order we add and subtract in. So I'm just going to grab those 3 things that I circled, and that's going to represent this thing right here. So that minus that and that all go into that delta G term. And then the things I didn't circle are all still left over. Okay? Now, do you see that? That products minus the total of the reactants. That's our delta G for the reaction. Now what can we do with the rest of that? So I like that delta G standard term. And by the way, that is the standard delta G. That we can look up in the book and take products minus reactants to the table. Then all this. I see some things in common, though, to all 3 of these terms that remain, that are colored. What do you see in common?
RT.
The RT is common to all 3 terms. So let's go ahead and try to clean this thing up. And I have pulled, so I've still got my delta G. That hasn't changed. The left side hasn't changed. My RT now, for the last 3 terms, has been pulled out. And I've just got whatever does not include the RT left inside of the parentheses. Yes, the following.
How do you know this works for like any reaction?
How do you know that it works for any reaction? As long as there are gases in there, and it's been shown to be accurate, and you're going to see what we get at the end, and what we get at the end is, man, it's well-founded, it works. And we'll do labs and we'll see that it works.
Okay.
Yes, Al?
Is it the partial pressure of them, or is it like the pressure?
Yeah, it's the partial pressure. So the pressure that just the hydrogen exerts, just the NH3. Yep. Yep. Okay. Now, one of the things that we know about logarithm, if I have 2 times the log of the pressure of ammonia, how could I rewrite that? What can I do with that too? It can be pressure squared, right? It's the same thing. So that's what I'm going to redo, is I'm going to take the 2 and put it as an exponent of the pressure, and the 3 and put that over here as an exponent of that pressure. So there's my 2 and there's my 3. That follows the properties of logs. This didn't have a coefficient, so I don't mess with that one, right? What else do you know about logs? If I have the log of this term minus the log of that term, what could I do to clean that up? Yeah, it could be the log of the quantity that divided by that, right? What if I'm subtracting 2 things? Divide both of them, right? That's where I'm going next. Yeah. So we're just doing all this algebra, and we eventually get an, I've carried the bottom equation over to the top. And so subtracting the logs just means divide those terms. It would be like that. The log of that whole quantity. Natural log. Just to remind you, the chemical equation for this reaction is 3H2s plus N2 yields 2NH3. So what I have here is the delta G of this reaction. Remember what delta G tells us? What does delta G tell us?
Free energy.
How much energy is either given off or taken in. Also tells us whether the reaction is spontaneous or not. So that's what this delta G is going to tell us. It's going to be the standard delta G, if everything was in standard conditions, plus RT times the natural log of that quantity. Okay, is there anything that you've learned in your chemistry experience that looks anything like this? The pressure of the product squared over the pressure of that cubed times that. What have you ever seen in chemistry? Let's go back to last year. Don't remember? Okay, it's fine. Let's keep going.
Oh.
We're going to rename this quantity Q, capital Q. And that Q represents what we call the reaction quotient. Now, you probably didn't do reaction quotient, but the next thing you're going to recognize. You may have, yeah. Nathan?
Is that the final equation?
Yes. Yes. This is the final equation. We're still going to continue to mess with this, but yeah, this is what that whole Gibbs equation, this has more physical meaning. So yeah, if you stopped writing anything down, the part in the box and then underneath it is worth your time to write that down. Q gives us an idea of where the reaction is in its progress. If Q is real small, well, at the beginning Q is 0 because you don't have any products at the beginning of the reaction. So you have products over reactants, and Q at the beginning of the reaction is 0. And as soon as the reaction starts to proceed, Q is going to go up because the more of this that's made, the less of these there will be, so that fraction continuously changes. At the end of the reaction, what is Q?
0.
Now at the beginning of the reaction it's 0 because you're going to have 0 over whatever the pressure of the reactants is. But at the end of the reaction, the products you're going to have made products, and what will the reactant pressures be? One of them at least should be 0. So you're going to have something over 0. What's that? Yeah, undefined, or infinity. Like Q would be infinity at the end of the reaction. Because it just goes up and up and up throughout the process of reaction. Okay? So we have this equation, and what does this tell us? Well, this term right here tells us whether the reaction is going to be spontaneous or not. What it doesn't tell us, though, is that all of the products are going to be made. The reaction might not make all the products that you expect it will. And so what happens if you don't get all the products that you expect it to? What happens if the reaction starts and it occurs spontaneously, but then stops before the reactants run out? Any of the reactants. What do you call that condition in a chemical reaction? When the reaction starts and it's making products, and then it doesn't continue, it just stops. And you still have some reactants there, but they're not reacting anymore. That's what equilibrium is. That's equilibrium. Now, the delta G, this term right here, is going to tell us whether the reaction is going to start heading toward equilibrium, but eventually this term will become 0. the point at which the products have the same free energy as the reactants do, that's where this term is going to become 0. And then when the point that this is 0, then that's the equilibrium point. That's where the reaction hits equilibrium. And before we move on, if I could just go back up here, you see a delta G term here and a delta G term here, and it may not be obvious to you right now. What's the difference between these two terms? This term right here is a constant. For every reaction, you can always look up the standard delta G value, and remember, standard conditions means that all your pressures of gases are 1 atmosphere, all your temperatures are 25 degrees, all your solutions are at 1 molarity. That's like the ideal conditions for a reaction. That's a constant. If you're not in ideal conditions, then that doesn't describe your delta G. You can still use that in this equation, but if you're not at those conditions, then you have to calculate this number. You have to find what point of the reaction you're in, that's Q, and you have to figure out what the temperature is and plug that in for T. So this term is a constant. You might want to write that down for yourself if that's not obvious to you. This term is constant. You can look it up, and you have to take products minus reactants for the table values, but that doesn't change. This term, though, does change. Throughout the reaction, the delta G is constantly changing, and the point at which this delta G hits 0, that's equilibrium. That means the reaction is not pushed to the right or to the left; it just stops. All right. So at equilibrium, the Q that we found right there, we're going to rename that thing. We call that K. Because K, the equilibrium constant, is the ratio of the products to the reactants, the pressures of their concentrations. So at equilibrium, Q is going to be renamed K. And so we can just do a little bit more math with this. This is the reaction's delta G at any other point other than equilibrium. And then as soon as you hit equilibrium, this term is 0. And then this Q is renamed K. So I've just replaced the Q with K. Now this is good only for equilibrium. If you're not in equilibrium, then Q just represents what the product to reactant ratio is. And so this equation, you have two things equal to 0. That means that if I just clean this equation up and move the RT natural log of K over to the other side, we have this. At equilibrium, you can find the K, the standard, the equilibrium constant for any reaction if you know the delta G, the standard delta G. So now we have delta G related to the equilibrium constant for a reaction. So as we've been going along, we have a relationship that we first learned about delta G, delta H minus T delta S. Delta G is also the delta G, the products minus the reactants. And now we have a relationship with delta G related to the equilibrium constant for a reaction. Most reactions that we deal with will come to equilibrium. They'll stop. They won't go to completion. Some will go to completion, like acid-base reactions, they'll go to completion. As soon as one of the reactants runs out, then we know we're done. But a lot of gas phase reactions, like when you have a gas plus a gas make another gas, I don't have a reaction up here, those often will stop before they're done. Before one of the reactants runs out, it just stops and it gets to equilibrium. Because you get to the reaction gets to its point of lowest energy, and then it doesn't have anything driving it one way or the other. It just stops. I have an analogy, a free energy equilibrium analogy that I'd like to share with you.
Who's got a birthday coming up?